it is consistent with the F theorem. So this is NR, and you have Monte-Carlo degreasing function in the large M limit. And if you want, so you can productively compute the subleading corrections. So to see the small mass regions if you want. Okay? But anyway, so what I want to say is that so this is Monte-Carlo degreasing and also positive. And yeah, this is consistent with the F theorem. Okay?
Sorry, those coefficients are universal in terms of the definition of the universal?
Yes. So okay, you can cancel this part by adding a term including the Riemann Rich scalar. But this cannot be but the other terms cannot be shifted by any counter terms. So you don't have any finite counter term. Okay. So in this sense, this is universal. Okay, so next I'd like to move on to the second topic. Okay, but is there any questions? Okay, so I will switch the subject. Okay, so far we consider the renormalization group and its relation to the entanglement entropy. But with the supersymmetries. So unfortunately, so even if you have a renormalization group flows from UV to IR, so usually it's very hard to compute the entanglement entropy, except for free fields. So if you want to know the information at the IR fixed point, where this is CT, so if this is interacting field series, then at least, yeah, I cannot compute the entanglement entropy for these series. But if you have supersymmetries, by using the localization techniques, you can compute the exact computations, exact partial function at the IR fixed point, or maybe at the UV fixed point. So thanks to the supersymmetries. So then my motivation is that so why don't you take advantage of supersymmetries to compute the entanglement entropy? Okay, so from now on, I'm going to consider entanglement entropy or Renyi entropy. So I'm going to talk about the Renyi entropy across D-2 dimensional sphere. I focus on spherical entanglement surface in CFTD. I only consider conformal field series. In this case, the Renyi entropy is given by sphere partial function, but here we have to put your theory on the n covering D sphere. So here I have a theta coordinate, theta, and I have circles. So this is D-2 dimensional sphere, and this is a circle parameterized by tau. Now tau has 2 pi m periodicity, and I call this geometry S and D. Okay, so if you focus on the conformal field theory and also spherical entanglement surface, then the Renyi entropy can be computed by the partial function. So given by the partial function of such a geometry, such a sphere. Okay, and if theory is free, so if theory is free, then you can compute this part. So you can compute a partial function on the n covering sphere, because this is just one loop determinant, one loop partial function. One loop determinant. is okay. But okay, on the other hand, okay, if we have supersymmetries, and if we focus on the entanglement entropy, so where n goes to 1, then so entropy, so S1 is equal to the log of the sphere Partial function, SD. So you know how to compute this guy. So we have already heard a nice talk by Sanjay. So in this case, if we have supersymmetries, then you can compute the entanglement entropy by localization. So you can compute Z, SD. By localization, you know the exact result. So the naive question is that, so can you compute the partial function on such a space for Suzy gate theories? So this is my very naive question. This was my naive questions. And it turns out that you cannot compute the exact partial function naively. It's because on this space, the supersymmetry is broken completely. Supersymmetry, so once, okay, so when n is equal to 1, then there is nothing, okay, because this space does not have any singularity, but for general n, then there appears a singularity at this point, so this becomes singular. And this singularity breaks supersymmetry completely. So even if you start with supersymmetric gate theories, unfortunately you cannot preserve any supersymmetries. Okay, so unfortunately Suzy is completely broken. On the n covering D sphere. So then, naively, you cannot compute the Rényi entropy for Suzy gate theories. But, so there is one way to recover supersymmetry. So to recover supersymmetries, you can turn on background gate fields or background fields. You can turn on the background fields. So if you have background fields, then if you are lucky, then you can preserve supersymmetries, a part of supersymmetries. Actually, in D equals 3, you have U1R symmetry. This is the R symmetry. And then you can turn on the U1R symmetry background gauge fields. So this is background gauge fields. And if you tune the background gauge field to be n-1 half, if you turn on the background gauge field along tau direction, so this is my tau direction. If you turn on some gauge field related to the R symmetry, since every field, scalar field and fermion field have different R charges. So this is kind of chemical potential for the R charge. Since the fermion and the scalar field have different R charges, you can compensate the difference. Okay, basically, so the reason why supersymmetry is broken is that scalar and fermion has different periodicity along tau direction. So they have different periodicity. But by tuning the chemical potential for R symmetry, then you can compensate them. So you can let them behave similarly, and you can recover the supersymmetries. Okay, so this is some typical background. Okay, so if you have such a symmetry,
here, n may not be an integer.
I'm sorry?
Doesn't the n need to be an integer or not?
Now, so in this case, n is just a real number. Yeah, thank you. So this is just a real number. N was originally just the integer, but I analytically continue n to the real number. Okay, so if we have such a background field, you can preserve supersymmetries, but it modifies the definition of the entanglement entropy or linear entropy. Okay, so you have two choices. So without background fields, you don't have any supersymmetries, and you cannot compute the exact partial function, and you don't get anything. So you don't get anything, or even for supersymmetric gauge series. But once you turn on the background fields, then so although you have to modify the definition of the linear entropy, you can compute them exactly thanks to supersymmetries. Okay, so now I'm going to define a supersymmetric linear entropy. Supersymmetric linear entropy. Okay, so this is my work with Itama. Okay, so definition of the supersymmetric linear entropy is very similar to the usual one. So here I have 1 over 1 minus n, and here I have log of the partial function of n covering D sphere. But here I turn on background fields to preserve supersymmetry. So this is a partial function in the presence of background fields. And so mostly so the definition is same. Okay, so this is the supersymmetric partial function. So the partial function. And I take the absolute value because only usually we take absolute value because the partial function can be complex number. Okay, anyway, then, so if you introduce such a quantity, then you can exactly compute this guy, supersymmetric partial function, on the n covering sphere. So you can compute this guy in 3 dimensions. So in 3 dimensions, so after computing the partial function by using localization technique, I'm not going into the detail, but the result is very interesting because this guy turns out to be the supersymmetric partial function on the Scarcity 3 sphere. So Scarcity 3 sphere has a parameter b. This is scarcity parameter, and b should be square root of n. So if you tune the scarcity parameter, then at the level of matrix model, so they are equivalent. Okay. So if you tune the scarcity parameter, then so this partial function becomes a partial function on the scarcity sphere. Okay. And similarly, in higher dimensions, d equal 4 and d equal 5.
Sorry, that was the observation, or
this is observation.
I see.
Observation. But probably there is an argument that in 3 dimensions you have as long as you preserve U1 square symmetry as a manifold, then the partial function is always given by the scarce sphere partial function. I mean, you have only one parameter deformation. And in our case, we have a U1 square symmetry. And similarly, okay, I focus on n equal 2 series. And in 4 dimensions, there is a very nice work by recently. And
presumably there will be some kind of exact deformation that takes you from the SDN to the squash 3 sphere.
Maybe, yeah. That's why you only have one deformation parameter. Yeah. But in our case, we literally evaluate the partial function on this space. Okay, in 4 dimensions, Oh, by the way, okay, so the SUSY Prussian function on sky sphere was computed by Somichi-san and Sanjay and Hama-kun. Okay. So, and in 4 dimensions, so it turns out that so the Prussian function is equal to the Prussian function on the ellipsoid. So it is usually called ellipsoid. So it has 2 deformation parameters, epsilon1 and epsilon2. But epsilon1 and epsilon2, the ratio is given by n. So this was recently computed by these gentlemen, Wang, Cho, and also another group, Crossley, Dyer, Sonner. And also in 5 dimensions, so we recently computed for n equal 1 theory. In 5 dimensions, you have scattered 5 sphere, and it is parameterized by 3 parameters, omega 1, omega 2, omega 3. But these are just 1, and this is 1 over n. Omega 1, only 1 parameter is given by 1 over n. So this is my recent work, and also independently found by Alday, Richmond, Sparks, and also my group, so Hama-kun and Gradin-kun. Okay, anyway, so although we consider a SUSY Prussian function on singular manifold, it turns out that it is equal to the SUSY Prussian function on the non-manifolds. In 3-dimensional case, we have scarce sphere. In 4-dimension, also we have ellipsoid. Oh, this was also the work by Somichi-san and Hama-kun. And in 5 dimensions, this is what I think done by various people, including Imamura-san and Lockhart and Baffa, I think. Okay, anyway, so we have an answer. Okay, so let me list a few properties of my superlinear entropy. Okay. Okay, so supersymmetry linear entropy is equal to the usual entanglement entropy when n equal to 1. Because when n equal to 1, we don't turn on any background fields. Okay, in this case, U1R gauge field vanishes when n equal to 1. So we don't add anything. So it is equal to the entanglement entropy. And in 3 dimensions, so we looked at the behavior near n equal to 1. So if you expand the superlinear entropy around n equal to 1, it starts with S1, and you have form like this. So the second term is proportional to n minus 1. But here, tau RR, so this is kind of universal coefficient. It appears in the 2-point functions of R symmetry current. I think this was mentioned by Zoho. Okay, so here you have U1 current, U1 R symmetry current. And if cell is conformal, then you have a universal coefficient. Also, another interesting case is the Lurgen limit. So in the Lurgen limit, so D equals 3 case with n equals 2 supersymmetries. Behaves as like this. So the n dependence simplifies in the Lurgen limit. So here we have n dependence, but in the Lurgen limit, independence is given by this. So here, so S1 is the usual entanglement entropy. And it's worth to mention that, okay, so this functional form satisfies the several inequalities to which the usual entanglement entropy, usual Renyi entropy satisfies. So for example, so the usual Renyi entropy satisfies inequality. So the Renyi entropy, if you take a derivative with respect to n of the usual Renyi entropy, it should be non-positive. But this function also satisfies this property. I think this is correct. And also, yeah, there are several properties the usual Renyi entropy satisfies, but all of them are satisfied by the supersymmetric Renyi entropy in the larger limit, at least. So somehow, although we turn on the background fields and we modify the definition of the Renyi entropy, so it shares some nice properties with the usual Renyi entropy. Okay. So I'm gonna. Okay. Oh, by the way, is there a question?
So does those properties imply that there are something reduced density?
Yeah, you can rewrite this definition by using the reduced density matrix, but in the presence of the chemical potentials. Okay, so I have to mention that. Okay, so my super Renyi entropy is one particular example of so-called charged Renyi entropy. So you can turn on a chemical potential. Okay, so usually, so we have to define the Renyi entropy. We can use the reduced density matrix. We take a trace of rho A to the n. But here, if you want, you can turn on chemical potential for some symmetry Q. So this is the so-called charged Renyi entropy. So introduced by Myers and his collaborators. But I don't remember all of the collaborators. But anyway, so this is called the charged Renyi entropy. And yeah, super Renyi is actually the one of the particular example. Okay, so let me slightly mention that. Okay, since I consider the larger limit, I'd like to mention that there is a holographic description of super Renyi entropy. Okay, so holographic description, holographic. Okay, so since we put the theory on n-covariant sphere, so we had a geometry of this type. Okay, we need to construct the holographic description. So we need to find the geometry, ADS geometry whose boundary has this structure. So we have to extend this structure to the bulk ADS space. But actually this is not good coordinate since we have to go around n times along tau direction. Oops. So I map this space by using conformal map. So I can map this space to S1 times hyperbolic space. So here I have S1 times D minus one-dimensional hyperbolic space. And so each slice I have a D minus two-dimensional sphere. So this is spatial slice. Okay, so now in this coordinate, it's very clear that this is nothing but the final temperature field theory on Ht minus 1. Okay, so we originally had a field theory on this complicated, or it's not so complicated, but n governing Z sphere. But after the map, so we have a final temperature system on D minus 1 dimensional hyperspace. So in this picture, it's much easier to construct the gravity dual of this space. Okay, so the gravity dual becomes as follows. The gravity dual is actually a black hole geometry. So this is S1 and this is hyperbolic space. But I extend this geometry to the ADS. So here I have ADS D plus 1 space. But since we are at final temperature, so we should have a black hole. Actually, we have a black hole horizon here. So this is my ADS radial coordinate R. And at R equal to RH, I have horizon. I have a black hole. And but we have to preserve supersymmetry somehow. So since we turn on background fields in the boundary side, so correspondingly we have to turn on some fields in the bulk side, and then it becomes, okay, this black hole becomes a charged black hole. This becomes BPS charged black hole, but it is so-called topological black hole in any space. So the name of topological comes from the fact that even for non-supersymmetric case, okay, if you turn off the charge, then you still have black hole horizon. So this is just nothing but the coordinate transformation of the pure AD space. Okay. And this black hole has mass m, but to preserve supersymmetries, we also have charge q, but they should be equal to preserve supersymmetries. And if you tune the temperature, black hole temperature, to be 1 over 2 pi m, since we want to consider such a geometry in the boundary side, so we tune the temperature, black hole temperature, to be 1 over 2 pi m, and computing the holographic free energy, or the Persian function, or classical, let's say, classical action evaluated on this geometry. So since we have AD-CFT correspondence, so AD-CFT correspondence tells us that the Persian function on, say, S1 times H t minus 1, but with periodicity 2 pi n, should be equal to e to the minus gravitational action. So this is gravity action, gravity on the black hole, geometry. So BPS black hole. By using this relation, so you can similarly compute the supersymmetric ray entropy from gravity calculation. And
sorry, how does the black hole manage to be supersymmetric and has finite temperature?
Right. Okay. First of all, even for usual topological black hole has supersymmetry because it is nothing but coordinate transformation, and also it has temperature because when you take n goes to 1 limit, you have temperature. And as you turn on the charge, then it changes the periodicity somehow. And okay, now you want to change the temperature first. Naively, you break supersymmetries. But since you have charge here, so you can compensate the periodicity of the fermion